The last thought paradox raises a profound question about the nature of consciousness and the experience of time at the moment of death. If a person's final conscious thought before death is the last subjective experience they ever have, does that moment, from their perspective, last forever? Our perception of time is tied to our awareness, and without a future, the last instant of consciousness could theoretically stretch into an eternal moment. This paradox suggests that a person on the verge of death might feel trapped in a frozen instant, never truly reaching unconsciousness in their own perception. It challenges the idea that death is an abrupt end rather than an infinite stillness. Similar questions arise in neuroscience and philosophy. Does the brain experience a final surge of activity, creating an illusion of time extending indefinitely? Could this explain near-death experiences, or the sensation of life flashing before one's eyes? Some interpretations suggest that in a subjective sense, a dying person may never experience the state of being dead, as their last thought remains their entire reality. The last thought paradox blurs the line between time, perception, and mortality, raising unsettling questions about the nature of existence and whether the final moment of life is truly the end, or an unending experience locked within consciousness itself. The confirmation bias paradox highlights how people unknowingly seek and interpret information that reinforces their existing beliefs, even when they think they are being objective. The paradox arises because the more we try to confirm our views, the less likely we are to challenge them, creating a self-reinforcing cycle. This bias shapes our decisions in politics, science, relationships, and everyday life. People selectively absorb information that supports their beliefs while ignoring contradictory evidence, leading to echo chambers where opposing viewpoints are rarely considered. The backfire effect makes it even worse. When faced with conflicting evidence, individuals often strengthen their original stance rather than reconsider it. Even scientists and professionals fall into this trap. Investors ignore warning signs about failing stocks. Doctors may misdiagnose by focusing on expected symptoms. And researchers might design studies that confirm their hypotheses. In the age of social media, algorithms further amplify confirmation bias by feeding users content that aligns with their views. Overcoming this paradox requires actively seeking opposing perspectives and questioning assumptions. However, even this effort can reinforce bias if people only acknowledge counter-arguments that still fit their broader worldview. The paradox ultimately shows how difficult true objectivity is and why critical thinking is a constant challenge. The paradox of the unexpected exam is a logical puzzle that challenges notions of surprise and self-referential reasoning. A teacher announces to a class that there will be a surprise exam next week, meaning students will not know which day it will occur until it happens. A student reasons that this is impossible. If the exam were scheduled for Friday, they would know by Thursday night, removing the surprise. If Thursday were the last possible day, the same logic applies, and they could rule it out. Following this reasoning backward through the week, the student concludes that a surprise exam is impossible. However, when the teacher gives the exam on an unexpected day, the class is still surprised, contradicting their logic. This paradox arises because the student's reasoning assumes complete certainty in eliminating possible days. But their logic itself creates the conditions for the surprise. It highlights limitations in predicting future events when self-referential logic is involved. The paradox has been studied in philosophy, mathematics, and game theory, as an example of how expectations and reasoning about knowledge can lead to paradoxical conclusions. The self-amendment paradox emerges when a rule or law has the ability to modify itself, leading to a logical contradiction. Imagine a legal system where a rule states, "All laws, including this one, can be amended." This implies that the rule itself could be altered or even removed. However, if it is removed, then it was never an absolute law to begin with. On the other hand, if a law states, "This law cannot be amended," but the system still allows amendments, its authority contradicts itself. This paradox is particularly significant in constitutional law, where amendment processes exist to modify legal frameworks. If a system permits changes to its fundamental rules, can it truly establish permanent laws? If an amendment process is used to eliminate the power to amend, does that invalidate the original system? These questions expose the fragile balance between flexibility and consistency in law, logic, and governance. The teleportation paradox challenges our understanding of identity and consciousness. Imagine a person stepping into a teleportation machine which scans their body, disassembles every atom, and transmits this information to another location, where a replica is instantly reconstructed. The paradox arises when we question whether the person who emerges at the destination is truly the same individual, or just an identical copy. Is the original person destroyed in the process, or does the teleportation preserve their consciousness? This paradox raises concerns about the nature of self and continuity of existence. If every atom is replaced and the consciousness is transferred, does the person in the new location truly retain the same identity? Or is it just a replica with the same memories and experiences, but no real continuity of life? The teleportation paradox prompts us to explore deep philosophical questions about personal identity, the mind-body connection, and what it means to exist as a unique individual. The Einstein-Podolsky-Rosen (EPR) paradox was proposed by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 as a thought experiment that challenged the principles of quantum mechanics. The paradox is based on the concept of quantum entanglement, where two particles can become so deeply connected that the state of one particle immediately affects the state of the other, no matter how far apart they are in space. This phenomenon appears to contradict the principles of local realism and causality, suggesting that information can travel faster than the speed of light, which Einstein famously referred to as spooky action at a distance. The EPR paradox raises the question of whether quantum mechanics provides a complete description of physical reality. Einstein and his colleagues believed that quantum mechanics was incomplete because it predicted outcomes that seemed to violate the principles of locality and causality, which had been foundational to classical physics. According to Einstein, there must be hidden variables that explain the phenomena observed in quantum mechanics, and these variables would restore the deterministic nature of physics. However, experiments conducted later, such as those by John Bell in the 1960s, showed that the predictions of quantum mechanics, including entanglement, are indeed correct, and they cannot be explained by any hidden variables that would make the system behave deterministically. This has led to the conclusion that quantum mechanics does, in fact, accurately describe the behavior of particles, even if it challenges our classical intuitions about space, time, and reality itself. The EPR paradox has played a crucial role in the development of quantum theory, highlighting the strange and non-intuitive nature of the quantum world, and deepening our understanding of how reality operates on a fundamental level. The twin paradox is a thought experiment in the realm of special relativity, first introduced by Albert Einstein, that highlights the counterintuitive nature of time as it relates to high-speed motion. In this paradox, a pair of identical twins are involved in a situation where one stays on Earth, while the other travels into space at near light speed, only to return years later. According to Einstein's theory, the twin who travels at such a high speed will experience time more slowly than the twin who stays on Earth. This is a result of time dilation, a phenomenon predicted by the theory of special relativity. The paradox arises when the traveling twin returns to Earth and reunites with their sibling. The twin who remained on Earth will have aged significantly more than the traveling twin. From the perspective of the traveling twin, however, it would seem as though it is the earthbound twin who is moving and thus experiencing the slower passage of time. This creates confusion about which twin should have aged less. The resolution to the paradox lies in the fact that the situation is not symmetrical. The traveling twin experiences not just constant motion, but also acceleration and deceleration, which breaks the symmetry between the two. According to special relativity, acceleration is an absolute effect, meaning the traveling twins' experience of time is affected by more than just their velocity. The earthbound twin, however, remains in an inertial reference frame throughout the entire process, so the time dilation effect only applies to the traveling twin. Mathematically, the time dilation experienced by the traveling twin is governed by the Lorentz factor, which calculates how much time slows down for an object moving at speeds close to the speed of light. The closer the velocity is to the speed of light, the greater the time dilation. This means that when the twins are reunited, the traveling twin will have experienced less passage of time, even though they perceive the earthbound twin as moving. This seemingly paradoxical situation can be fully explained when accounting for the effects of acceleration and the fact that the two twins have experienced different reference frames. The twin paradox not only challenges our classical understanding of time, but also serves as a demonstration of the non-intuitive nature of special relativity. It shows that time is not an absolute universal constant, but is relative to the observer's motion. Though the paradox seems perplexing at first, it is a well-understood consequence of the theory of relativity and has been supported by experimental evidence, such as the observed time dilation of atomic clocks on fast-moving jets. The twin paradox remains one of the most famous and thought-provoking examples of how the universe behaves differently at high speeds. The bootstrap paradox is a mind-bending time travel paradox that challenges our understanding of cause and effect. It occurs when an object, piece of information, or event exists without ever being created, forming a self-sustaining loop with no clear point of origin. The paradox raises the question: if something is passed back in time and later retrieved in the future, but it was never originally created, where did it come from? A classic example of the bootstrap paradox involves a time traveler who takes a famous book back in time and gives it to a young writer, who then copies and publishes it as their own. The book becomes famous, inspiring future generations. Years later, when the time traveler grows up, they take a copy of the book back in time again, repeating the cycle. In this scenario, the book was never written. It simply exists in an endless loop, with no true point of creation. This paradox applies not just to objects, but also to ideas and knowledge. Imagine a scientist in the future discovers an important equation and then travels back in time to give it to a younger version of themselves. The younger scientist studies the equation, grows older, and eventually discovers it again, ensuring the cycle repeats forever. But if the equation was never independently derived, does it have an actual origin? The bootstrap paradox highlights fundamental issues with time travel, particularly regarding causality and the nature of information. If an object or idea is caught in a time loop with no clear beginning, does it truly exist in the conventional sense? The paradox suggests that time travel could create self-contained loops where certain events occur without any external cause, seemingly violating the principle that every effect must have a cause. Some physicists argue that the paradox could be resolved through quantum mechanics or the many worlds interpretation, where each iteration of the loop exists in a separate branching timeline. Others suggest that reality might self-correct in a way that prevents such paradoxes from occurring, similar to the Novikov self-consistency principle, which proposes that time travel may be possible but cannot change events in a way that creates logical contradictions. The bootstrap paradox is frequently explored in science fiction, appearing in movies, TV shows, and books where objects, knowledge, or even people appear to have no true origin. It challenges our perception of time, causality, and free will, leaving open the question of whether time loops like this could ever exist in reality. The quantum suicide paradox is a thought experiment that explores the strange implications of quantum mechanics, particularly the many worlds interpretation. It raises questions about consciousness, probability, and whether an observer can experience their own death. The paradox is based on Schrödinger's famous thought experiment involving a cat in a box, whose fate is tied to the random decay of a radioactive atom. However, in this version, the experiment involves a human observer, making it far more unsettling. Imagine a scientist sitting in front of a quantum-based gun that is triggered by the decay of a subatomic particle. According to quantum mechanics, before the particle decays, it exists in a superposition of states, both decayed and not decayed. The gun is designed to fire only if the particle decays. Every time the experiment is run, the quantum mechanics interpretation suggests that two realities branch off. In one, the scientist is shot and dies, while in the other, the particle does not decay, and the scientist survives. Under the many worlds interpretation, the universe splits into different realities every time a quantum event occurs. This means that in some universes, the scientist is killed, but in others, they always survive. From the perspective of an external observer, the scientist has a 50% chance of survival with each trial. However, from the perspective of the scientist, they never experience their own death. In every timeline where they die, their consciousness ceases to exist, but in at least one timeline, they continue to survive indefinitely. This implies that the scientist would only ever experience a universe where they miraculously avoid death every single time, no matter how many times the experiment is repeated. The paradox raises profound questions about the nature of reality and consciousness. If the many worlds interpretation is correct, does it mean that an individual observer is effectively immortal, always continuing to exist in some branch of the universe? This concept is sometimes referred to as quantum immortality. However, it remains purely theoretical, as there is no way to test or verify the subjective experience of an observer who continues surviving in an increasingly improbable timeline. Critics argue that the paradox relies on an extreme interpretation of quantum mechanics and does not account for the fact that biological consciousness may not persist in the way the thought experiment suggests. Others propose that even if the observer avoids death in some universes, they would eventually experience physical and mental degradation, making immortality meaningless. The quantum suicide paradox remains one of the most mind-bending ideas in physics and philosophy. It challenges our understanding of fate, probability, and the nature of self-awareness, making us question whether reality is truly deterministic or if infinite possibilities unfold with every quantum event. The arrow of time. Paradox challenges our understanding of why time appears to flow in one direction, from past to future, despite the fundamental laws of physics being time-symmetric. In most physical equations, time can theoretically move forward or backward without issue. However, in everyday life, we experience an irreversible progression of events. Water spills, but never unspills. Eggs break, but never reassemble. And people age, but never grow younger. This paradox arises from the contradiction between time symmetry in physics and the observable, irreversible nature of time. One key explanation comes from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This principle gives time its apparent direction, because natural processes tend to move from order to disorder, rather than the other way around. For example, a hot cup of coffee left in a room cools down over time as heat disperses, but it never spontaneously heats up again. This increase in entropy is what defines the arrow of time from a thermodynamic perspective. However, if the fundamental laws of physics do not distinguish between past and future, then why was the universe in a low entropy, highly ordered state in the first place? The paradox suggests that the universe must have started in an extremely special, low entropy condition at the Big Bang. But why would this be the case? Some physicists argue that this is simply a brute fact of our universe, while others propose deeper explanations, such as the idea that entropy decreases in certain regions of the universe beyond our observable horizon. Another perspective comes from cosmology. Some theories suggest that time's arrow may not be a universal rule, but rather a consequence of our local conditions. One hypothesis, known as the two-headed arrow of time, proposes that in certain regions of the cosmos, or in a mirror universe on the other side of the Big Bang, time could flow in the opposite direction. If true, this would mean that in some parts of the universe, beings could experience time moving backward from our perspective, though they would still perceive their own time as progressing normally. Additionally, quantum mechanics raises further questions about the nature of time. Some interpretations of quantum mechanics, such as the Wheeler-DeWitt equation, suggest that at the most fundamental level, time may not exist at all. Instead, time could be an emergent property that arises from entangled quantum states. If this is true, then the arrow of time might not be a fundamental feature of the universe, but rather a macroscopic illusion resulting from large-scale interactions. The arrow of time paradox remains one of the most profound mysteries in physics. It forces us to ask why we remember the past, but not the future, why causality seems to function in only one direction, and whether time is an inherent aspect of reality or merely a perception of human consciousness. As theories about entropy, cosmology, and quantum mechanics evolve, scientists continue to search for a deeper understanding of why time flows the way it does, and whether it might behave differently in other parts of the universe, or under extreme conditions. The information loss paradox challenges one of the fundamental principles of physics, the idea that information can never be destroyed. According to quantum mechanics, all physical processes are reversible in theory, meaning that if you had complete knowledge of a system at one point in time, you could reconstruct its past state. However, when information falls into a black hole, it appears to be lost forever, violating this principle. This paradox raises deep questions about the nature of black holes, quantum mechanics, and the fundamental laws governing the universe. The problem arises from the way black holes interact with their surroundings. According to general relativity, a black hole forms when a massive star collapses under its own gravity, creating a region from which nothing, not even light, can escape. Any matter or energy that crosses the event horizon is trapped forever, seemingly erasing all information about its original form. However, in the 1970s, Stephen Hawking discovered that black holes are not completely black. They emit radiation due to quantum effects at the event horizon. This radiation, now called Hawking radiation, slowly causes black holes to evaporate over time. The paradox comes into play because Hawking radiation is purely thermal, meaning it carries no information about what originally fell into the black hole. If a black hole eventually evaporates entirely, the information about everything that fell into it seems to vanish from the universe. This contradicts quantum mechanics, which states that information must be preserved. This creates a fundamental clash between the two pillars of modern physics: general relativity and quantum mechanics. Several possible solutions to the paradox have been proposed. One idea is that information is not lost, but somehow encoded in the Hawking radiation in a highly scrambled form. This would mean that while the information is not truly destroyed, it is effectively inaccessible in practice. Another possibility is that the information is stored at the event horizon itself, an idea supported by the holographic principle, which suggests that all the information inside a black hole might be represented on its surface. A more radical proposal is that information escapes through quantum entanglement, where particles inside and outside the black hole remain connected even after the event horizon separates them. Some theories suggest that black holes may leave behind a remnant containing the missing information, or that the information is somehow funneled into a parallel universe. In 2019, physicists studying quantum gravity found new mathematical evidence suggesting that information might indeed escape in a subtle way. This research hints that black holes could subtly release information over time, resolving the paradox without requiring new physics. However, no definitive answer has been reached, and the debate continues. The information loss paradox is more than just an abstract problem. It touches on the fundamental nature of reality, time, and the limits of human understanding. If information can be truly lost, it could force a major revision of quantum mechanics. On the other hand, if information is ultimately preserved, it may lead to a deeper theory that unites quantum mechanics and gravity. The resolution of this paradox could be one of the most important discoveries in modern physics, offering insights into the true nature of space, time, and the universe itself. The proton decay paradox arises from the contradiction between theoretical predictions and experimental evidence. Many grand unified theories, GUTS, suggest that protons, the building blocks of atoms, should eventually decay over immense timescales. However, despite decades of experiments, no proton decay has ever been observed. According to these theories, protons should break down into lighter particles, like positrons, and pions, with a predicted half-life far longer than the age of the universe. Yet, extensive studies in underground detectors, such as the Super Kamiokande in Japan, have failed to detect a single instance of proton decay. This absence of evidence challenges key ideas in particle physics and raises fundamental questions about the stability of matter. If protons truly never decay, it would suggest that our current understanding of unification theories is flawed. On the other hand, if they do decay, but at an even slower rate than expected, we may need more sensitive experiments to detect them. Resolving this paradox is crucial to understanding whether matter is truly eternal, or if the universe will one day dissolve into energy as protons slowly vanish over unimaginable timescales. The Schrödinger's cat paradox is a thought experiment designed by physicist Erwin Schrödinger to illustrate the strange implications of quantum mechanics, particularly the concept of superposition. The scenario involves a cat placed inside a sealed box, along with a radioactive atom, a Geiger counter, a vial of poison, and a mechanism that will release the poison if the Geiger counter detects radiation from the atom's decay. According to quantum mechanics, until the box is opened and observed, the atom exists in a superposition of both decayed and undecayed states. Because the cat's fate is directly linked to the atom, it too must exist in a superposition, both alive and dead at the same time, until an observer looks inside. This paradox highlights the conflict between quantum mechanics and our classical understanding of reality. In everyday life, objects exist in definite states, but in the quantum world, particles can exist in multiple states simultaneously. The paradox raises deep questions about when and how quantum superposition collapses into a single reality, a process known as wave function collapse. Different interpretations of quantum mechanics attempt to explain this, including the Copenhagen interpretation, which states that observation causes the collapse, and the many worlds interpretation, which suggests that both outcomes occur in separate, parallel universes. Schrödinger originally devised this paradox to criticize the idea that an object could exist in two contradictory states at once. Yet experiments on quantum particles have shown that superposition is a real and measurable phenomenon. While the paradox is hypothetical, it has inspired decades of debate in physics and philosophy, shaping discussions on the nature of reality, consciousness, and the role of observers in the universe. The dark matter paradox challenges our understanding of the universe's structure. Observations of galaxies reveal that their outer regions rotate at the same speed as their inner regions, defying the expected gravitational influence of visible matter. According to Newtonian physics, galaxies should be tearing apart, yet they remain stable. This inconsistency suggests the presence of an unseen force, now referred to as dark matter. Despite its critical role in explaining cosmic motion, dark matter has never been directly observed. It does not emit, absorb, or reflect light, making it invisible to traditional detection methods. Scientists infer its existence only through gravitational effects on stars and galaxies. Over decades, numerous experiments have attempted to identify dark matter particles, but no conclusive evidence has emerged. The paradox deepens when alternative theories are considered. Some propose modifications to the laws of gravity rather than invoking an unknown substance. Yet, no alternative model fully accounts for all observed cosmic phenomena as effectively as dark matter does. If dark matter is real, why has it remained undetectable? If it is not, what else explains the universe's unexplained gravitational forces? The dark matter paradox remains one of the most perplexing mysteries in modern physics. The Higgs boson mass paradox arises from the puzzling fact that the Higgs boson, a fundamental particle responsible for giving mass to other particles, has a much lower mass than expected based on quantum field theory. According to calculations, quantum fluctuations should cause the Higgs boson to have an enormous mass, far greater than what was observed in experiments at the Large Hadron Collider. However, in reality, the Higgs boson was found to have a mass of about 125 gigaelectron volts, a value that seems unnaturally fine-tuned. This paradox challenges our understanding of fundamental physics. If the Higgs boson's mass is not the result of some yet unknown mechanism, it would require an extraordinary degree of cancellation between quantum effects, something that seems highly unlikely. One possible resolution is supersymmetry, a theoretical framework that suggests every known particle has a heavier partner that counteracts these quantum fluctuations, keeping the Higgs boson's mass at a reasonable level. However, no evidence of supersymmetric particles has been found so far. Another possibility is that the Higgs boson's mass is determined by anthropic selection, meaning that only in a universe where the Higgs has this precise mass could complex structures like galaxies, stars, and life exist. If true, this would suggest our universe is just one of many in a multiverse, each with different fundamental constants. The Higgs boson mass paradox remains an open question in physics, challenging scientists to uncover whether the Higgs mass is a product of deeper principles or simply an unexplained cosmic coincidence. The quantum gravity paradox arises from the fundamental incompatibility between quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles on the smallest scales, while general relativity describes gravity and the structure of space-time on large scales. Both theories have been experimentally confirmed to extreme precision in their respective domains. Yet when applied together, such as in the extreme conditions of black holes or the early universe, they produce contradictions. One major issue is that quantum mechanics treats forces like electromagnetism as being mediated by particles called bosons, but attempts to describe gravity in the same way lead to infinities and non-physical results. Unlike other forces, gravity affects space-time itself, which quantum mechanics struggles to describe in a consistent way. Additionally, quantum mechanics relies on a fixed background of space-time, while general relativity says space-time is dynamic and influenced by mass and energy. The paradox is most evident in black holes, where gravity is immensely strong. According to general relativity, anything that falls into a black hole is lost beyond the event horizon, but quantum mechanics suggests that information cannot be destroyed. This leads to the black hole information paradox, an unresolved mystery in physics. Various theories attempt to resolve the quantum gravity paradox, such as string theory, which proposes that particles are actually tiny vibrating strings that unify gravity with quantum mechanics. Another approach is loop quantum gravity, which suggests that space-time itself is made up of discrete, quantized units. However, no definitive experimental evidence has yet confirmed either theory. Solving this paradox would revolutionize our understanding of the universe, potentially revealing the true nature of space, time, and reality itself. Until then, the search for a theory of quantum gravity remains one of the biggest challenges in modern physics. The omnipotence paradox questions whether absolute power is logically possible. A common version asks, can an omnipotent being create a rock so heavy that it cannot lift it? If yes, then it lacks the power to lift it. If no, then it lacks the power to create it. Either way, omnipotence seems self-contradictory. Similar dilemmas arise with concepts like an irresistible force meeting an immovable object. If an omnipotent being can create an immovable object, then it cannot move it, contradicting its power. If it cannot create such an object, then its power has limits. Some argue that omnipotence should be defined as the ability to do anything logically possible rather than anything imaginable. This avoids contradictions, like creating square circles. Others suggest true omnipotence should transcend logic itself, but this leads to further paradoxes. Religious and philosophical perspectives attempt to resolve the paradox in different ways. Some claim omnipotence means having the greatest possible power, rather than an ability to do the impossible. Others argue an omnipotent being could define what is logically possible. Ultimately, the omnipotence paradox challenges the very concept of unlimited power and forces us to reconsider whether true omnipotence is a coherent idea or an inherent contradiction. The paradox of the ravens, also known as Hempel's paradox, is a famous problem in logic and the philosophy of science that challenges our understanding of how evidence confirms hypotheses. It arises from the logical equivalence of statements and leads to an unintuitive conclusion about what counts as valid scientific evidence. The paradox begins with the statement, "All ravens are black." Logically, this is equivalent to saying, if something is not black, then it is not a raven. This means that any observation confirming one statement should also confirm the other. At first, this seems straightforward. Seeing black ravens should support the idea that all ravens are black. However, because the logically equivalent statement also implies that every non-black, non-raven object supports the hypothesis, the paradox suggests that observing a green apple or a red book should also provide evidence that all ravens are black. This seems absurd, as we do not usually consider unrelated objects as proof of a claim about ravens. One possible resolution comes from Bayesian probability, which suggests that while such observations technically offer confirmation, their impact is minuscule compared to directly observing black ravens. The paradox highlights fundamental issues in the philosophy of science, questioning how we determine what counts as meaningful evidence and how logic interacts with our intuitive reasoning. The new riddle of induction, introduced by philosopher Nelson Goodman, challenges our understanding of how we justify inductive reasoning, the process of making generalizations based on past observations. It builds upon traditional problems of induction, but introduces a deeper issue regarding the criteria for distinguishing between valid and invalid predictions. Goodman presents the paradox using the concept of the word GRU. Suppose we define GRU as a color that applies to objects that have been observed before a certain future time and are green, but after that time, they appear blue. By this definition, all emeralds observed so far are both green and GRU. However, this creates a dilemma. If past observations of green emeralds support the belief that all emeralds are green, they should also support the belief that all emeralds are GRU. If the GRU property were valid, then at some future point, emeralds should turn blue. Yet we do not expect this to happen. The paradox forces us to question why we accept some predicates, like green, as meaningful for induction, but reject others, like GRU. This problem highlights the difficulty in defining what makes a generalization valid and exposes a fundamental issue in scientific reasoning. Unlike traditional induction problems, which question whether past observations justify future predictions, Goodman's riddle asks how we determine which patterns are reasonable to follow in the first place. It remains a key challenge in the philosophy of science and logic, influencing debates on how we justify knowledge and prediction. The faint young sun paradox arises from a contradiction between astrophysics and geological evidence. Based on our understanding of stellar evolution, the sun was about 30% less luminous around 4 billion years ago than it is today. This should have resulted in a much colder Earth, likely frozen over, making it inhospitable for liquid water and life. However, geological records suggest that Earth had liquid oceans and a relatively warm climate at that time, with evidence of early microbial life. The paradox raises the question: how did Earth remain warm enough to support liquid water and early life, despite the sun being significantly fainter? Several hypotheses attempt to resolve this contradiction. One possibility is that greenhouse gases like carbon dioxide and methane were present in much higher concentrations in the early atmosphere, trapping enough heat to compensate for the weaker solar output. Another theory suggests that Earth may have absorbed more solar radiation due to differences in cloud cover, atmospheric composition, or albedo, reflectivity. Some researchers also consider the role of geothermal heating from Earth's interior. Despite these potential explanations, no single solution fully resolves the paradox, and the exact mechanisms that kept early Earth warm remain an area of active research in planetary science and climatology. The Planck scale paradox arises from the fundamental incompatibility between quantum mechanics and general relativity at extremely small scales. The Planck length, about 1.6 times 10 to the negative 35th power, and the Planck time, about 5.4 times 10 to the negative 44th power, represent the smallest meaningful units of space and time, beyond which current physical theories break down. According to quantum mechanics, space and time should behave smoothly even at these tiny scales. But general relativity suggests that at such extreme conditions, space-time itself may become chaotic, possibly forming quantum foam, a turbulent sea of fluctuating energy. The paradox arises because our best physical theories, quantum mechanics, which governs the smallest scales, and general relativity, which governs gravity and large structures, are fundamentally incompatible at the Planck scale. In this regime, the gravitational effects of quantum fluctuations should be significant, potentially creating microscopic black holes or distorting space-time so severely that classical notions of space and time cease to exist. However, no existing theory fully describes what happens in this regime, making it one of the greatest mysteries in physics. Potential solutions to this paradox include string theory, which proposes that fundamental particles are not point-like, but instead tiny vibrating strings, and loop quantum gravity, which suggests that space-time itself is quantized into discrete units. However, until experimental evidence confirms a viable theory of quantum gravity, the true nature of physics at the Planck scale remains an open question. The confirmation. Bias paradox highlights a contradiction in human reasoning. The more we believe we are objective, the more likely we are to reinforce our own biases. Confirmation bias causes people to seek, interpret, and remember information that supports their existing beliefs while ignoring contradictory evidence. This paradox deepens when individuals try to be unbiased but unknowingly strengthen their biases instead. One striking effect is the backfire effect, where encountering opposing evidence doesn't weaken a belief, but strengthens it. Rather than reconsidering their stance, people become more entrenched. This fuels selective exposure, where individuals surround themselves with like-minded sources, reinforcing their views. Even scientists, trained in critical thinking, sometimes interpret data in ways that confirm their hypotheses rather than challenge them. This paradox affects decision-making in politics, science, business, and personal relationships. Investors may ignore warning signs in a company they believe in, while people in relationships reinforce stereotypes by only recalling experiences that support their views. Escaping this paradox requires actively engaging with opposing perspectives, questioning our own certainty, and being open to change. However, even our efforts to be objective can sometimes reinforce bias, proving that no one is truly free from it. Recognizing this reality is the first step toward genuine critical thinking. The infinite mirror. Paradox arises when two mirrors face each other, creating an endless reflection that seems to extend into infinity. Each mirror reflects the image of the other, producing a series of reflections that appear to recede forever. But does this infinite series of images actually exist? Or is it just an illusion? In theory, the reflections should continue indefinitely, but in reality, they eventually fade. This happens because mirrors are not perfectly reflective. With each bounce, a small amount of light is absorbed or scattered, gradually dimming the reflections until they disappear from view. Additionally, imperfections in the mirrors and the interference of external light sources disrupt the perfect continuity of the images. This paradox also raises deeper philosophical and scientific questions about infinity and perception. If each reflection is a copy of the previous one, where does the real image end and the illusion begin? Could this be a visual metaphor for recursion, self-reference, or even the nature of infinite regress in logic and philosophy? On a quantum level, the paradox becomes even more interesting. Since light behaves both as a wave and a particle, at extremely small scales, quantum effects may prevent the reflections from truly being infinite. The infinite mirror paradox serves as a fascinating example of how the concept of infinity, which seems straightforward in theory, often runs into limits when applied to the real world. The dream paradox challenges our understanding of reality by questioning whether we can ever be certain that we are not dreaming. Dreams can feel vivid, coherent, and immersive, often indistinguishable from waking life until we awaken. This raises the unsettling question: if we can mistake dreams for reality while dreaming, how do we know we are not in a dream right now? Philosophers such as René Descartes explored this paradox, famously asking whether any experience could be trusted as real. If all our senses can be fooled in dreams, what guarantees that they are not deceiving us at this very moment? This uncertainty forms the basis of skeptical arguments about the nature of perception and consciousness. Neuroscience offers some insights, showing that dreams originate in the brain and involve the same neural pathways that process real-life experiences. However, this does not resolve the paradox. It merely suggests that reality, too, is a construct of the brain. Lucid dreaming, in which a person becomes aware they are dreaming and can sometimes control the dream, adds another layer to the puzzle. If we can be conscious inside a dream, does that mean our current consciousness could also be part of an elaborate simulation or illusion? This paradox also appears in literature and pop culture, notably in films like Inception, where layers of dreams blur the boundaries of what is real. Ultimately, the dream paradox forces us to confront the limits of human perception and the possibility that reality itself might be nothing more than an incredibly convincing illusion. The rebirth paradox is a thought experiment that explores the nature of life, death, and identity, especially in the context of reincarnation or hypothetical future technologies. The paradox questions whether a person who is reborn or recreated after death would still be the same individual. In its simplest form, the rebirth paradox arises from the idea of reincarnation, where the soul or consciousness of a person is believed to be reborn in a new body. The paradox asks, if the body and the environment are entirely new, how can the person be the same as their previous incarnation? Would they retain their memories, experiences, and identity, or would they be an entirely different person, despite the continuity of consciousness? In a more modern context, the paradox is often explored in relation to the possibility of mind uploading or digital immortality. If a person's mind is scanned and then uploaded into a new artificial body or a digital environment, would they still be the same person? Or would they simply be a copy of the original with no real continuity of self? Even if the original mind's memories and personality are perfectly replicated, is the resulting entity truly the same person, or merely a new one with the same traits? This paradox also ties into the philosophical debate of personal identity. What makes someone the same person over time? Is it continuity of consciousness, memory, or perhaps a more metaphysical quality, such as a soul or core essence? The rebirth paradox invites us to reflect on the nature of selfhood, the persistence of identity, and whether true rebirth or resurrection is even possible without altering our fundamental understanding of who we are. The infinite lottery paradox revolves around the idea of an infinite series of independent events, such as drawing a lottery number. In this paradox, imagine an infinite number of lottery tickets, each with an equal chance of winning. If there are infinite tickets, it seems that every number should eventually be drawn, and one ticket must be the winner. However, this creates a paradox. If you are asked to pick a ticket in this infinite lottery, how can you possibly predict which one will win? No matter which ticket you choose, it feels as if any of them could potentially win, and there's no way to ensure your ticket will be the winning one. The randomness inherent in the infinite number of tickets seems to suggest that you can never be certain about which number will emerge victorious. The paradox goes deeper when considering the practical implications of infinite possibilities. In a finite lottery, we understand that with a fixed number of tickets, there's a clear chance of winning based on the number of tickets sold. However, in an infinite system, the concept of a chance, or probability, becomes more abstract and difficult to comprehend. As every ticket has an infinite possibility of winning, yet no guarantee that any one ticket will win. This paradox challenges our intuition about probability, randomness, and what it means to have an infinite set of possible outcomes. It raises questions about how we define chance in a truly infinite universe, and whether or not concepts like winning even make sense in such a scenario. The reverse Pinocchio paradox is a thought experiment that plays with the concept of truth and self-awareness, much like the famous Pinocchio paradox. The paradox is a twist on the idea of self-referential statements, statements that refer to themselves. In the classic Pinocchio story, Pinocchio's nose grows whenever he tells a lie. Now, imagine a world where, instead of his nose growing when he lies, it shrinks whenever he tells the truth. This would mean that every time Pinocchio speaks the truth, his nose would get smaller, and every time he lies, it would grow. The paradox arises from the implications of this new rule. If Pinocchio says, "My nose is shrinking," the statement implies that he is telling the truth, so his nose should shrink. However, If his nose is shrinking, it means he must be telling the truth, so the statement holds. On the other hand, if his nose shrinks because he's telling the truth, then his statement becomes true. But it leads to an infinite loop of self-validation. It's as if the truth and the shrinking nose are locked in a paradox that can't resolve itself. The reverse Pinocchio paradox challenges our understanding of self-referential logic, truth, and how the process of validating a statement or claim can spiral into uncertainty. It's a compelling exploration of how even simple concepts like lying and truth-telling become complicated when combined with self-referential loops. The paradox questions the nature of truth in a context where it seems like it cannot exist independently of the very statement that defines it. The missing dollar paradox is a classic riddle that plays with our perception of logic and arithmetic. It is often used to demonstrate how human intuition can be easily misled when handling simple mathematical problems. The paradox begins with a group of 3 people who go to a hotel and decide to share a room. The cost of the room is $30, so each person contributes $10, giving a total of $30. Later, the hotel manager realizes that they had overcharged them by $5. The actual room rate is $25. The manager gives $5 to the bellboy and asks him to return it to the 3 guests. The bellboy, unsure of how to split $5 evenly among 3 people, decides to keep $2 for himself and return $1 to each guest. Now, each guest has paid $9, since they originally paid $10 but received $1 back. That means the total amount they have paid is 3 guests times $9 equals $27. The bellboy has kept $2, so if you add that $2 to the $27, you get $29. But wait, they originally paid $30, so where is the missing dollar? The paradox is that the problem has been presented in a misleading way, which causes confusion. The key to resolving it lies in the way the remaining $27 is distributed. Of the $27, $25 goes to the hotel for the cost of the room, and the remaining $2 is kept by the bellboy. So, there is no missing dollar at all. The riddle creates the illusion of a paradox by encouraging you to add the bellboy's $2 to the $27, when instead, you should be thinking about how the total of $27 is made up, the room cost and the bellboy's share. The missing dollar paradox is a useful illustration of how careful attention to detail is necessary when dealing with seemingly simple arithmetic. It shows how our mental shortcuts and assumptions can lead to faulty conclusions, even in basic mathematical scenarios. The unstoppable force versus immovable object paradox is a thought experiment that explores a contradiction between 2 hypothetical entities, an unstoppable force and an immovable object. The paradox asks what happens when these 2 entities, each with extreme and opposing properties, come into conflict. An unstoppable force is defined as one that cannot be resisted, no matter the obstacle, while an immovable object is one that cannot be moved by any force, no matter how powerful. The paradox arises when we try to imagine a scenario where these 2 meet. If the unstoppable force can't be stopped, it should be able to move the immovable object. But if the object can't be moved, the force can't affect it. This creates a logical contradiction. This paradox challenges our understanding of infinite power and the limits of physical reality. It highlights that in the real world, nothing is truly immovable, and no force is truly unstoppable, as all things are subject to the laws of physics. The paradox also reveals the limitations of concepts like infinity, which don't truly exist in the physical world. Ultimately, the unstoppable force versus immovable object paradox serves as a reminder of how extreme concepts can break down when examined through the lens of reality, showing that both absolute power and immobility cannot exist in the same universe. The Sorites paradox, also known as the paradox of the heap, challenges our understanding of vague concepts, particularly when defining when a collection of small parts becomes a whole. The paradox is typically illustrated using a heap of sand. If you have a heap and remove a single grain, it is still a heap. If you keep removing grains one by one, at what point does it stop being a heap? Similarly, if you start with a single grain and keep adding one at a time, when does it become a heap? The problem arises because language and logic struggle to handle gradual changes in quantity or quality. Terms like heap, bald, or tall lack precise boundaries, leading to contradictions when applying strict reasoning. This paradox highlights fundamental issues in philosophy, linguistics, and even law, where vague definitions can lead to ambiguous conclusions. Various solutions have been proposed, such as fuzzy logic, which allows for degrees of truth rather than strict binary classifications to handle vagueness in a more nuanced way. The infinite library. Paradox is inspired by Jorge Luis Borges' concept of the Library of Babel and explores the implications of an infinite collection of books containing every possible combination of letters and words. Imagine a library so vast that it holds every book that could ever be written, including exact copies of famous works, books filled with gibberish, and even volumes that contain your own life story, both true and false versions. The paradox arises because, within such a library, knowledge becomes meaningless. While it theoretically contains all information, finding the right book would be impossible, as it would be buried in an infinite sea of nonsense. Additionally, if every possible variation of a book exists, can any book be considered truly original? This paradox questions the nature of knowledge, meaning, and authorship, raising deeper philosophical issues about how we define truth and information in an infinite system. The preface paradox is a logical problem that arises in epistemology, particularly concerning beliefs and rationality. It describes a situation where an author writes a book and, before publishing, includes a preface in which they acknowledge that despite their best efforts, some errors may still be present. However, at the same time, the author believes every statement in the book to be true. The paradox emerges because these two beliefs, one, that each individual statement in the book is true, and two, that at least one statement is likely to be false, seem contradictory. How can someone rationally hold both beliefs at once? This challenges our understanding of rationality, knowledge, and consistency. The preface paradox illustrates the limits of certainty in human knowledge and suggests that accepting some level of fallibility might itself be a rational stance, even when it leads to apparent contradictions. The Sleeping Beauty paradox is a thought experiment in probability that challenges our understanding of belief and self-locating uncertainty. The scenario is as follows. Sleeping Beauty is put to sleep on Sunday. A fair coin is flipped, and if it lands on heads, she will be woken up on Monday, and then allowed to wake up naturally on Wednesday, with no memory of Monday's events. However, if the coin lands on tails, she will be woken up on Monday, put back to sleep with her memory erased, and then woken up again on Tuesday under the exact same conditions, believing it is Monday. Regardless of the outcome, she is asked the same question upon waking. What is the probability that the coin landed on heads? The paradox arises because there are two competing ways to analyze this probability. One position, known as the half view, argues that since the coin is fair, the probability should remain 1/2, just as it was before she went to sleep. The other position, called the third view, suggests that because there are 3 possible wake-up moments, Monday heads, Monday tails, and Tuesday tails, and she has an equal chance of waking in any of them, the probability of heads should instead be 1/3. This paradox has led to extensive debate in philosophy and probability theory, because it forces us to reconsider how probability should be assigned when memory loss and repeated identical experiences are involved. It also raises questions about how we should reason in situations where we have limited self-locating information, making it one of the most famous puzzles in modern probability theory. The causal loop. Paradox is a puzzling concept in time travel and causality, where an event causes itself to exist in a closed loop, without any clear point of origin. This paradox arises when an effect becomes its own cause, leading to a situation where something seemingly comes into existence from nothing. One famous example is the case of a time traveler who goes back in time and gives Shakespeare a copy of his own plays. Shakespeare then copies them and takes credit for writing them. Centuries later, when the time traveler is born, he finds the plays, travels back in time, and delivers them to Shakespeare. The question then arises, who actually wrote the plays? Since the plays exist without ever being originally created, they exist in a loop with no beginning. Another example is the idea of a person going back in time to inspire their younger self to become a time traveler. If the older version is responsible for the younger version's path, then where did the original decision come from? The causal loop paradox challenges our understanding of cause and effect. It suggests that under certain conditions, such as time travel, causality could be self-contained and cyclic, breaking the normal expectation that every effect must have an independent cause. Some physicists suggest that causal loops might be possible under certain interpretations of quantum mechanics or relativity, but they remain purely theoretical. This paradox raises deep questions about free will, determinism, and the nature of time itself. The paradox of fiction presents a thought-provoking dilemma about human emotions. It asks, how can we experience genuine emotions for things that we know aren't real? When watching a film, reading a book, or engaging with any form of fiction, we often feel deeply moved. We may feel afraid when a character is in danger, sad when something tragic happens, or happy when a character achieves something meaningful. But the paradox arises from the fact that we are fully aware that these characters and events are not real. So, how can we experience these emotions as though they were? The paradox can be broken down into 3 seemingly contradictory claims. People do indeed experience genuine emotions toward fictional characters and events. In order to have real emotions, we must believe the subject of our emotions is real. We know that fictional characters and events are not real. If all three of these claims are true, it creates a contradiction. How can we feel sadness, fear, or joy for something that we know to be a product of imagination? After all, when we interact with the real world, our emotions are tied to real, tangible things, such as people, events, or objects. So why do we respond emotionally to things that don't exist outside of our minds? One possible explanation for the paradox is that our emotional responses to fiction are similar to how we react to hypothetical or imagined scenarios. For example, when watching a fictional tragedy unfold, our brains may temporarily suspend disbelief, allowing us to engage with the characters and events as though they were real. This is similar to how we might emotionally react to an imagined future event, even though we know it hasn't happened yet. The feeling of sadness or fear might come not from the reality of the event, but from its emotional weight and significance. Another resolution could be that we don't react to fictional characters themselves, but to the ideas or themes they represent. For instance, a character might symbolize the loss of a loved one or the struggle for justice. Even if we know the character is fictional, the emotions that come with those themes are real and applicable to our own lives. A tragic story may remind us of our own experiences with loss, making the emotions we feel for the character a reflection of real-world emotions, rather than a response to the character's existence. Some philosophers and psychologists also suggest that the paradox reveals an interesting feature of our cognitive processes. Humans have the ability to engage in what is called fictional belief, where we momentarily accept a fictional world as real, even if we know it's not. This temporary suspension of disbelief is a complex mental state that allows us to experience emotions and engage with fictional narratives on a deeper level. It may also explain why we can feel emotional connection with characters or events that we know to be entirely fictional. The paradox of fiction continues to challenge our understanding of emotions, belief, and our connection to storytelling. It asks important questions about how we interpret the world around us and the ways in which we engage with the ideas and themes presented in fictional worlds. Despite the paradox, it seems that our emotional lives are deeply intertwined with stories, real or imagined. As we continue to explore human psychology and philosophy, the paradox will likely remain an intriguing topic of discussion for those curious about the nature of our emotional experiences. The unexpected exam. Paradox is a philosophical puzzle that plays with logic and expectations. A teacher tells the class there will be an exam during the week, but it will be a surprise, meaning the students won't know the day in advance. The teacher adds that it will occur on a weekday. The twist is that the students are supposed to be surprised, but they begin to reason that this is impossible. Here's how the students think. If the exam hasn't happened by Thursday, it must happen on Friday. But then the students would know the day of the exam, making it no longer a surprise. So they conclude the exam can't happen on Friday. Using the same logic, they eliminate Thursday, Wednesday, and even Tuesday. Because once they reach a certain day, the rest of the week becomes predictable. By the time Monday rolls around, they've convinced themselves the exam can't happen at all. But then, on one of the days, the teacher gives the exam anyway, and the students are, to their surprise, caught off guard. The paradox arises because, despite their reasoning, the exam still occurs as a surprise, contradicting their expectations. The paradox challenges our understanding of expectations and how knowledge about the future can influence what we think we know. Even when we think we have logically deduced something, we can still be surprised. It underscores how our understanding of the future, influenced by logic, can sometimes be flawed or incomplete, leading to unexpected outcomes. The teleportation paradox arises from the hypothetical idea of teleportation, a common trope in science fiction. Imagine you step into a machine that teleports you to a distant location. The process involves scanning your entire body and mind, breaking down every atom, and transmitting that information to another machine where you are reassembled in the exact same form. At first glance, this sounds like a simple process of transporting matter from one place to another. However, the paradox emerges when we ask a few deeper philosophical and metaphysical questions. Does the person who emerges from the machine after teleportation remain you? One interpretation is that, in the teleportation process, the original you is effectively destroyed in the first location, while a copy of you is created elsewhere. While this copy might have your exact memories and experiences, the question is whether this new person is actually you or a perfect duplicate. The original individual is gone, and the reassembled person, despite being physically identical, might be a different consciousness altogether. So, if you die in the process of teleportation, are you truly alive on the other side? Or has your consciousness ceased to exist, and someone else with your memories simply takes your place? This paradox raises questions about identity, continuity of consciousness, and what it means to be you. If teleportation destroys and recreates the person, is it still the same person, or are they merely a clone? The paradox challenges our ideas about personal identity, existence, and the relationship between consciousness and the physical body. The McTaggart's time paradox stems from philosopher J.M.E. McTaggart's argument about the nature of time. McTaggart proposed that time, as we understand it, is an illusion, and that our conventional perception of time as a linear, progressive flow is fundamentally flawed. He presented this argument through a paradox based on two views of time: the A series and the B series. The A series represents time as a flow of events, with a dynamic nature. Events are constantly moving from the future, through the present, to the past. In this view, everything that happens is either future, present, or past, and the passage of time is intrinsic to our experience of reality. This view aligns with our intuitive understanding of time, where we see things happening, being, and then passing. On the other hand, the B series is more static, where events are ordered by a relationship of earlier than or later than. In this view, time does not have the same flow. Instead, it is a mere ordering of events in relation to one another, with no need for events to be experienced as future or past. Time is seen as a series of fixed events. McTaggart's paradox arises when he suggests that the A series and the B series are both necessary for time to make sense. If time is defined only in the A series, it would require a constantly changing state, which McTaggart argues is logically inconsistent because any event cannot simultaneously be future, present, and past. The A series itself involves contradictions because as soon as an event becomes present, it instantly becomes past, thus erasing any meaningful difference between future, present, and past states. Because of this, McTaggart concluded that time, as we experience it, cannot be real, because it requires an impossible combination of contradictions. If both the A series and B series are necessary to define time, and neither can stand alone, time itself must be an illusion. The paradox challenges the way we think about time, suggesting that the flow of events we experience may not correspond to anything real about the universe, but rather to a constructed perception of reality. This paradox has profound implications for our understanding of time, change, and the nature of existence itself. The forbidden number. Paradox is a mathematical phenomenon that arises when certain numbers are restricted based on specific rules, such as divisibility, set membership, or other defining properties. At first glance, it may seem straightforward that forbidding numbers, according to a set rule, simply reduces the set in a predictable way. However, paradoxical consequences emerge when the remaining numbers exhibit unexpected properties, distributions, or behaviors that defy intuition. A key element of this paradox is that even after removing an infinite subset of numbers from an infinite set, the remaining numbers often still form an infinite set, yet with altered mathematical characteristics. These changes can affect summation, density, divisibility, and structural patterns, leading to results that appear contradictory or counterintuitive. In some cases, forbidden number restrictions can even lead to logical inconsistencies or force new mathematical definitions to resolve anomalies. This paradox is significant in number theory, set theory, and combinatorics, as it challenges our understanding of how mathematical structures behave under constraints. By studying the effects of forbidden numbers, mathematicians gain deeper insights into the nature of numerical patterns, infinity, and the fundamental properties of mathematical sets. The paradox of the Planck of Carneades is a philosophical dilemma that arises when moral responsibility and survival instincts come into direct conflict. At first glance, it may seem clear how justice should be applied in a life or death situation, but paradoxical questions emerge when ethical principles clash with the fundamental drive for self-preservation. A key aspect of this paradox is that even in situations where legal and moral frameworks provide clear guidelines, extreme circumstances can challenge conventional judgments. The act of taking another's life for survival may be seen as both an unavoidable necessity and a punishable crime, leading to interpretations that appear contradictory or difficult to reconcile. In some cases, legal doctrines have attempted to account for such scenarios, while others uphold the absolute nature of moral and legal responsibility. This paradox is significant in ethics, law, and moral philosophy, as it forces a deeper examination of how justice, survival, and human nature intersect. By analyzing cases like the Planck of Carneades, philosophers and legal scholars gain greater insight into the complexities of moral reasoning, the limits of legal responsibility, and the profound ethical challenges posed by life or death decisions. நாற்பதாவது. The paradox of the false alarm is a philosophical and logical dilemma that arises when frequent false alarms undermine the reliability of warnings. creating a situation where people may fail to respond appropriately when a real threat occurs. At first glance, it may seem logical that warnings should always be issued when potential danger is detected. However, paradoxical consequences emerge when repeated false alarms lead to desensitization, skepticism, or outright disregard for future alerts. A key element of this paradox is that while warnings are meant to protect people by prompting action, excessive false alarms can have the opposite effect, causing individuals to ignore or mistrust critical warnings, even when they are genuine. This phenomenon is observed in various contexts, including emergency systems, cybersecurity threats, medical diagnoses, and even social behavior. The balance between caution and credibility becomes increasingly difficult to maintain, leading to outcomes that appear contradictory or counterintuitive. This paradox is significant in psychology, risk management, and decision theory, as it highlights the challenges of maintaining trust in warning systems while avoiding unnecessary panic. By studying the effects of false alarms, researchers gain deeper insights into human behavior, perception of risk, and the complex relationship between warning mechanisms and real-world responses. The information paradox is a profound puzzle at the intersection of quantum mechanics and general relativity, questioning whether information is truly preserved in the universe. Much like the conservation of energy, the conservation of information is a foundational principle in physics. Yet, under certain extreme conditions, particularly near black holes, this principle appears to break down, leading to a paradox with far-reaching implications. The core of the paradox lies in the tension between two well-established theories. Quantum mechanics insists that information cannot be destroyed. Every quantum process, no matter how chaotic, should be theoretically reversible. General relativity, on the other hand, suggests that anything falling into a black hole vanishes beyond the event horizon, never to return. If information is truly lost in this way, it would upend the very framework of quantum theory and create inconsistencies in how we understand entropy, causality, and the flow of time. Efforts to resolve the paradox have led to groundbreaking theoretical developments. Proposals like Hawking radiation suggest that black holes slowly evaporate, potentially releasing information in a scrambled form. Other ideas, such as the holographic principle or the concept of firewalls, attempt to preserve information by reimagining the structure of space-time itself. Despite these efforts, the paradox remains unsolved, continuing to inspire debate and exploration. Understanding the information paradox is more than an abstract theoretical exercise. It is central to unifying the laws of physics. By probing this mystery, researchers hope to discover deeper truths about the universe, pushing the boundaries of what we know about reality, gravity, and the quantum world. The paradox of tolerance is a philosophical dilemma that challenges the limits of open societies, questioning whether absolute tolerance can ultimately lead to its own downfall. At first glance, it seems intuitive that a tolerant society should accept all viewpoints, even those that oppose tolerance itself. However, this principle creates a contradiction. If tolerance is extended to the intolerant, it risks enabling forces that could erode or even destroy the very foundation of tolerance. This paradox, first articulated by philosopher Karl Popper, suggests that in order to maintain a tolerant society, one must be willing to restrict intolerance. If intolerance is allowed to spread unchecked, It may exploit the freedoms of an open society to suppress opposing views, leading to the rise of authoritarianism or extremism. On the other hand, enforcing limits on intolerance risks contradicting the very ideals of free expression and pluralism that tolerance seeks to uphold. Attempts to resolve this paradox often involve striking a balance between free speech and protective measures against harmful ideologies. Some argue that society should tolerate all ideas, but remain vigilant against those that incite violence or seek to undermine democratic principles. Others advocate for proactive intervention against intolerant movements before they gain power. Despite ongoing debate, the paradox remains highly relevant in discussions on democracy, human rights, and the ethical responsibilities of free societies. Understanding the paradox of tolerance is crucial for navigating the challenges of modern pluralistic societies. By examining its implications, we can explore the delicate equilibrium between openness and protection, ensuring that tolerance does not become the very mechanism of its own destruction. Newcomb's paradox is a decision theory problem involving a predictor with near-perfect accuracy. The decision maker chooses between two boxes. Box A is transparent and always contains 1,000. Box B is opaque and contains either 1 million or nothing, depending on the predictor's prior decision. If the predictor foresees the decision maker taking only box B, it places 1 million inside. If the decision maker is predicted to take both boxes, box B is left empty. Choosing only box B results in 1 million if the predictor is accurate. Choosing both boxes guarantees at least 1,000, but risks. Box B being empty. Causal decision theory argues past events are fixed and recommends taking both boxes. Evidential decision theory prioritizes statistical outcomes and favors. Taking only box B. Functional decision theory sees decision-making and predictions as linked and supports taking box B. The paradox questions rationality, free will, and the nature of prediction. The birthday paradox is a probability theory problem that demonstrates the counterintuitive likelihood of shared birthdays in a group of people. In a group of 23 people, there is a greater than 50% chance that at least 2 share the same birthday. With 57 people, the probability exceeds 99%. The paradox arises because people often assume the probability should be much lower, but the number of possible birthday comparisons grows rapidly with group size. The probability is calculated using the principle of complementary counting, determining the chance that no 2 people share a birthday and subtracting from 1. The birthday paradox is widely used in probability theory cryptography and hashing algorithms. The grandfather clock paradox is a thought experiment in the context of time travel and causality. It poses a scenario where a person travels back in time and accidentally prevents their grandfather from meeting their grandmother, or causes their grandfather's death before the time traveler is born. If this happens, the time traveler could never exist to travel back in time in the first place, creating a paradox where the traveler both does and does not exist. This paradox challenges our understanding of time, causality, and the potential consequences of time travel. It illustrates the contradictions that arise when actions in the past seem to interfere with the existence of the person making those actions. The grandfather clock paradox is often discussed in philosophy and theoretical physics, especially when exploring the implications of time travel and its consistency with the laws of physics. The paradox of the infinite staircase is a thought experiment that explores the concept of infinity in a physical space. It imagines a staircase that ascends infinitely, with each step spaced in such a way that although there are always steps to climb, one could never reach the top. The paradox highlights the challenge of conceptualizing infinity in practical terms. In this scenario, a person would never reach the end of the staircase because the number of steps continues to increase without bound. The paradox explores the tension between our intuitive understanding of physical spaces and the abstract concept of infinity. It raises questions about the nature of infinity, time, and motion, suggesting that infinity, although a useful concept in mathematics, does not have a clear or intuitive representation in the real world. The paradox of the infinite staircase is often used to discuss the philosophical and mathematical implications of infinity, particularly in relation to movement, progress, and the limits of human understanding. The self-reference paradox occurs when a statement or proposition refers to itself in a way that leads to a contradiction or logical problem. One of the most famous examples is the liar paradox, which involves the statement, "This statement is false." If the statement is true, then it must be false, as it claims. But if it's false, then it must be true. This creates an endless loop where the statement can't consistently be classified as either true or false. Self-reference paradoxes are important in fields like logic, philosophy, and mathematics because they challenge the foundations of systems of logic and set theory. They demonstrate that certain self-referential statements can lead to inconsistencies or contradictions, highlighting limits in formal systems and the complexity of self-referential reasoning. Self-reference paradoxes are central to discussions in Gödel's incompleteness theorems, where Gödel showed that in any sufficiently powerful formal system, there will always be true statements that cannot be proven within the system itself, partly due to self-referential constructions. The paradox of choice is a concept in psychology and decision-making theory, which suggests that while having some choice is essential for well-being, too many options can lead to anxiety, dissatisfaction, and difficulty making decisions. The idea, popularized by psychologist Barry Schwartz in his 2004 book, The Paradox of Choice, argues that when individuals are presented with too many options, they may experience feelings of overwhelm, regret, or fear of making the wrong choice. Research shows that as the number of choices increases, people may feel less satisfied with their decisions, even if they make a good choice. This can lead to choice overload, where the abundance of options prevents individuals from making a decision or leads to regret after making one. The paradox highlights the idea that more choice doesn't always lead to more happiness or better outcomes. The paradox of choice is particularly relevant in consumer behavior, technology, and marketing, where an abundance of options can sometimes reduce the overall satisfaction of customers. The nocebo paradox is the opposite of the placebo effect. It refers to a phenomenon where negative expectations or beliefs about a treatment or outcome lead to harmful or unpleasant side effects, even when the treatment itself is inert or has no actual harmful properties. The term nocebo comes from the Latin word nocere, meaning to harm. In the nocebo paradox, when individuals expect negative effects, their mind can trigger physical symptoms or worsening of their condition simply because they anticipate harm. This psychological effect can cause real, measurable health outcomes, such as headaches, nausea, or fatigue, even though no actual harmful substance or treatment is involved. The nocebo effect is often seen in medical contexts, where patients may experience side effects of a drug they believe will cause harm, even if they receive a placebo or a treatment with no known side effects. This paradox highlights the powerful connection between the mind and body, and how expectations can influence health outcomes. The paradox of perfect prediction refers to a situation where the ability to perfectly predict future events leads to paradoxical or undesirable outcomes. It often involves the idea that knowing the future with absolute certainty can undermine free will, decision-making, or the nature of events themselves. For example, if someone can predict the outcome of an event with complete accuracy, the prediction may influence the behavior of those involved, potentially altering the course of the event and making the prediction less relevant or even invalid. In other words, the act of knowing the future can change it in ways that make it impossible to truly predict in the first place. This paradox raises questions about determinism, free will, and the limits of knowledge. If every decision is already determined or can be predicted, it challenges the concept of personal agency and the meaning of choice. The paradox often appears in discussions of time travel, causality, and even in the context of machine learning and artificial intelligence. The paradox of the immortal executioner is a thought experiment that explores the logical and ethical contradictions associated with immortality and punishment. In this paradox, the executioner is granted immortality, but is tasked with executing individuals for a crime they have committed. The paradox arises when the immortal executioner is ordered to execute someone who, upon death, would be forced to live forever and suffer eternally. If the executioner cannot kill or harm an immortal being, in the normal sense, the act of execution would become an endless cycle where the person continues to suffer without the possibility of final death. The paradox challenges our understanding of punishment, ethics, and the nature of immortality. If immortality means an eternal existence without the possibility of escape, then execution, intended to end a person's life, becomes meaningless, as it cannot truly result in death or freedom from suffering. This paradox raises questions about the consequences of immortality and the potential moral dilemmas faced in a world where eternal life could be imposed. The paradox of the forgotten memories is a thought experiment that explores the conflict between memory, identity, and the passage of time. It suggests a scenario where someone forgets critical memories that shape their identity, but by forgetting, they paradoxically retain a sense of self or continuity, even though they are no longer the same person they once were. In this paradox, the act of forgetting might seem to break the connection between a person's past and their present self, as memories are integral to the way we understand and define our identity. However, despite losing these memories, the person still feels as though they are the same individual, which raises the question, if memories are lost, does the person's identity remain intact? The paradox challenges our understanding of identity by suggesting that memories, while important, may not be the sole foundation of the self. If a person can forget critical parts of their past and still maintain a sense of continuity, it calls into question what truly constitutes personal identity. This paradox can also be applied to scenarios involving amnesia or trauma, where individuals forget significant aspects of their lives, yet continue to experience a sense of self. It highlights the complex relationship between memory, consciousness, and identity.